Hi. How are you? I will. Okay. So the deal is this for that plan for the day. I do want to work on test corrections to the second page. I gotta say the last class didn't get through it all, and so we'll have to finish the test corrections tomorrow. But if we hold to the same form, we probably won't get to questions on homeworks again today, which means that 27 and 28 will both carry over till tomorrow. And tomorrow you might actually have 3 homeworks we need to go over, 27, 28, and 29. That said, tomorrow's not a lesson, so I think it will be all okay. I hope you're keeping up. Please don't fall into the trap that some fall into, and that's, oh, Mr. Rickman's behind on grading, so I can block my homework tonight. Tomorrow you might have a bit of a bad wake-up call because we will get caught up tomorrow. If you don't do 29 tonight, you're going to be taken on later. All right? So, what are we what? What are we doing? Oh, tomorrow? So, commonly, once in a while, I will pause for AP practice on stuff you've learned, or extra practice on stuff you learned, or a little deeper level on stuff you learned. It's pretty calm. All right? Questions about where we're headed? Are you ready to go? Are you feeling sharp? No? Okay. Well, good thing today is going to go so well. I'm going to make this so clear that you will have no problem with it, even if you're not on your game completely. So the lesson is differentials. What does differential mean to you? Nothing to you. It means nothing to you, yes? All right, then let's start with vocabulary. One big idea of calculus we talked about is we take the change between 2 points. That's delta y over delta x, right? Right. We then talked about getting those 2 points closer and closer together. Once you get the points so close together, then it starts to become more abstract, tiny difference. Then we stop calling it delta y and delta x, and we start calling it dy and dx. Those are differentials. dy and dx are differentials. Now, in the derivative, we look at how those compare to each other. How does y change with respect to x, the slope or the rate of change between the two, the rate of change. Today, we're just going to focus on one of them. How much does y change? You still have to take into account how fast it's changing, and then how much x is changing, and that'll tell you how much y is going to change. So you could boil this down to it's kind of a proportion level. I know that if normally y changes 5 units to every x change of 1 unit, then if I changed x by 2 units, then y would change by 10 units. It's kind of just a proportional thing at one level. It can be a little more complicated, but let's keep it simple. All right. So, first of all, vocabulary. When I say differential, you say dy or dx. All right, those are differentials. All right. Let's talk then about rates of change and then separating the differentials. Based on the rate at which y equals f of x equals x cubed plus x, I do that when I want to use both notations. Based on how fast it's changing at x equal 2, if I then increase x by 1 unit, how much will y change at that point? Let's start with translating this. The rate at which the function is changing at x equal 2. Is that change over an interval, average rate of change, delta y? Or is that change at a point, dy? dy dx. That's rate of change at a point. That's derivative. That's all code for derivative, yes? At a specific point. So please tell me, what is the derivative generally? Okay, and then what's the rate of change specifically at 2? Thirteen, right? You all see where I come from. Okay, now let's kind of rephrase this. That means dy dx at 2, another way to write f prime at 2 is to say dy dx, the derivative, at 2, is 13, and I'm going to call it a ratio. 13 is the same as 13 over 1. So in terms of answering the question, at that rate of change, if x increases by 1 unit, I would expect the rate of change in y to change by 13 units. That seems like a lot of change in y. For just one little move over in x, I'm changing y by 13. Why is that? So much change. Because it's a cube. The cube grows fast, right? Think of when you go from 1 cubed to 2 cubed, you're going up by 7. Or from 2 cubed to 3 cubed, you're going up by from 8 to 27. So it seems like it's logical. Now, question is, if this is how much the function actually, is this the function, how much the changes actually by going to x equals 3? I'm really having a hard time speaking of it. If not, why are we off? Well, at 2, what is the function equal to? 2 cubed plus 2 is 10. And by going to 3, I'm actually getting 3 cubed plus 3, which is 30. So what I would call the true change was actually 20, not 13. So then that begs the question, well, why is that off? I expected it to change by 13 units when I went from 2 to 3. Instead, it changed by more. Why the error? Why the error in my expectation of change? Think of a cube here. When I found the change at 2, I was saying, oops, let me call it this way. When I found the change at 2 and said, all right, I expect it to change 13 units per 1 unit in 1, did it stay that steep after I left 2? Or did it start to get even steeper after I left 2? All right, now, so because of the virtue of the curve, it's not linear, it doesn't stay that same rate of change everywhere like a line would. Because we are curving, it actually started going steeper, and so y actually changed by more than I expected it to. That happens, and so that's why you're going to be off a little, but because the derivative is so friendly, it's actually used in engineering quite a bit to estimate change. It's not the exact change, but it's a great estimate. We'll get to that in a second. First, though, consider this question. Try this one on your own. Based on the rate of change of that function at 9, how much would you expect y to change by when x decreases by 1? Try it on your own. See if you're following along. And if you're not, then that means I need to teach it better. Hey, how are we doing? What did you say? You have an answer for me. Shout out your answer. It can be wrong. What's -1/6, I heard? Okay, that's great. Now, you could look at this as saying the rate of change at that point is 1 to 6. Some like to say leave it 1/6, and that means that if x changes by 6 units, y would change by 1 unit. Some people might say, you know what's better for me is if I call this 1/6 over 1, then if x changes by 1 unit, y would change by a 6th of a unit. And if x changes by -1, then y would change by -1/6. You with me? But in terms of where we're headed, consider this. What if I had the ratio of change is 1/6, and I want to know how much y is going to change by? If I want to know how much y is going to change by, I don't want to compare anymore. I want to just say y will change by this. Well, algebraically then, that would mean I move that change in x over. So I take the rate at which y is changing with respect to x, multiply it by an amount of change in x, and I get an amount of change in y. So for this problem, the rate of change at that point is 1/6. I'm changing x by -1 because of the decrease, and so y would change by -1/6. Now again, that's my expectation of if it stayed the same everywhere, then that's how much it would change by. But again, this is a curve, so it probably won't stay that same rate of change, and I might be a little off, and it might change by something a little different, but it's a good estimate. Are you with me so far? Follow-up questions? Okay. All right then, let's talk developing the general idea here. You can see it's in the box there, but I'm going to show you how it comes about. A picture is, to me, the best illustration of this. Say you took a curve, whatever it might look like, f of x, and I want to talk about call this a first point here. Okay, I want to compare the secant slope between that point and one close by, and the tangent slope at that point. Over here. Okay. Are you about there picture-wise? You good? Now, in terms of the slopes, on the secant line, I could actually say, based on that, this truly went from this point to that point. The change from that y to that y, that's how much it truly changed by. So you'll see me refer to that as delta y, true change in y, how much it really did change by. This then would be horizontal change from one point to the other. That obviously then is delta x. Now I want to compare that to if I took how fast it was changing at this point and it stayed that much same rate of change, how would it have changed? Now if I want to talk instantaneous rate of change, this red line, then the tangent line is more dy dx, right? I want to compare the same amount of change. So this to here, I'm going to also say is the same for dx. You can see though that the y's between the original point and the tangent line at that point is different. Now that's the tangent line change in y, so that's dy. Are you with me? All right, now consider this. If we talked about if the 2 points are relatively close together, then the slope between that red line and blue line, they're pretty close. So we could say then that the slope of the secant line, which is true change in y between points over true change in x, is pretty close to dy dx. And I'm just for the fun of it going to introduce that this is the same as the derivative at that. Actually, I'm going to call that x initial if you don't mind instead of x1. The derivative at that point. The secant slope between 2 points is pretty close to the derivative at that first point. You with me? All right. Now, the goal of the lesson is to try and figure out, all right, based on calculus, how much would I expect y to change by? Well, if I take this equation and multiply delta x over, then delta y, or the change in y, would be something like the rate of change at that point times an amount of change in x. How fast y and x are changing relative to each other, times how much x we decide to change, will tell me how much y would decide to change. And that would then be the same as I would also have to multiply each of these components by delta x, so something like that, yeah? Are you with me? Are you with me? Okay. Now, you can see from the picture that we decided we're going to make the x change the same x points for either the tangent line or the curve. So you can see from the picture that delta x and dx are the same. I'm just looking at the same gap for both. If delta x and dx are the same, then I'm going to take this previous step, and instead of delta x, I'm going to say, let's call that dx. And instead of that delta x, I'm going to call that dx. That's where then this, with a little whoosh, whoosh, comes from. Delta y is approximately equal to dy, which is f prime at some initial point dx. Now that's, ooh, scary. In plain old English, it just means the change in y is approximately equal to the rate of change, a ratio of change in y with respect to x. Yeah, let's just go the rate of change times an amount of change in x. To figure out how much y will change, I'll just say, all right, well, how fast is y changing with respect to x? How much are we going to change x by? And that'll see how much y will change. Now, numerically, this makes a little more sense, but before we go there, I want to make sure you know how to do one of the Saxony kind of problems, and then we'll go to the numbers. This is a pretty typical problem you might see in the homework. You're given this function, y equals this big mess, and I want to get you some derivative practice, so that's why I made it a big mess. And you're finding dy, not dy dx, just dy. Well, don't get pooped out. Dy obviously means you need some calculus in it, right? How do you get a dy? You take derivatives. The problem, though, is derivatives are dy dx. Okay, well, that's great. I can take the derivative, but then how do I answer the question? Dy then is just move that over and say the change in y will be the derivative, which is the rate of change, then times some amount of change in x. But they never actually asked me to do a numerical calculation. If it changes this much, how much? You're just going to take the derivative and move the differential dx over. So take the derivative, and let's do a quick check to see how you're doing on your derivative technique, it's called. Those of you who are athletes or musicians appreciate the importance of technique. What is the derivative of sine? Cosine of x. What is the derivative of e to the x? E to the x. And then hardest one of the bunch is the derivative of 3. If you were going to help somebody who's been absent a week, how would you explain the safest way to go about it? What? Yeah, if you do a rewrite, even if it's just a mental rewrite, convert that to x to a power, and a root means 1/2, and a denominator means negative. So as a power, that's really 3x to the negative 1/2. Then the power rule goes smoothly. The power rule derivative is negative 3/2. Negative 1/2 comes down. 3 times negative 1/2 is negative 3/2. And you reduce the exponent by 1, so now it's negative 3x, right? And then the dx is that. Please do make sure you have parentheses because you're dealing with math teachers here. They are picky about that stuff. It's dx times the whole quantity, not just the last thing. You follow? Let's look at the application of this. This is a pretty big idea of calculus, so I actually will be teaching this over 2 or 3 different lessons. This is a starting application, and we'll get to more later. But let's call it good after this. So say I had a cube that I was measuring, and I put the ruler to the cube, and I found that the length of each edge is about 8 centimeters. Remember, cubes, all the edges are the same. Unfortunately, as happens with paper rulers especially, my ruler is a little deformed, the corners are a little bent, so I could be off. In fact, my measurement of the edge could be off as much as a millimeter, or 41 centimeters. Now this then is the idea. If I then use that measure of the side to find something else, like the volume or the surface area, won't that error then carry through to those later calculations? Yeah, that's called propagated error. Okay, it's error based on previous error. So the deal is this: I could actually find the true possible error, but in engineering, it's sometimes not feasible to do so, and you want to use a differential to estimate the error, and they're actually, on small scales especially, pretty doggone accurate. Now this one, we can probably find the true error because it's not too complicated, but we're going to practice using differentials. I'm going to do one for the volume with you, and then you'll try to do the same idea on the surface area, and hopefully you'll see how it works and it'll go well. All right, so check this out. If I wanted to figure out how much my volume could be off by my edge being off, then really I want to find the change in the volume that happened by going from 8 to 8.1 if I had error. You follow? Now, here's where the differential comes in. This is approximately equal to, instead of delta V, I'm going to use dV. Okay, that's the differential. Besides dy and dx, there are also differentials of lots of things. dV, dr, ds. It's just a small change in whatever the variables are. All right. Now, remember back to the previous, we said that dy is the derivative at a good initial point, dx. Unfortunately here, we're not dealing with y and f, we're dealing with volume. So let's actually go off to the side, pause for a second, and get a volume equation established in our mind. What's an equation for volume of a cube? X cubed, side cubed, you could use S cubed, that's fine. X, I'm just using X to represent the side. You agree though that the volume of a cube is X. Okay. Then in terms of the notation we're going to use, there is no F here. We're going to use the derivative of V prime. Now it's not just generally what's the rate of change everywhere. I want to know how fast is it changing at that point I'm using as a reference point. I'll come to that in a second, but it is at some point, and then times how much my x or my side is going to change by. This is crucial. Always. This should always be your starting point. This is required. I absolutely build points in for it. That is like the thesis of your paper. Without that, you're just writing crap with no idea of where it's headed, right? So that to me is important. Let's get into the details now. V prime, what is it? 3x squared, okay? The function is x cubed, so the derivative is 3x squared. Now, right here, I'm going to write an evaluation bar. I'm going to say to the person reading it, all right, that's my derivative. I showed you what the derivative is. And then I'm going to say, here's where I'm going to find it at. I want to find how fast this could change at what reference point. Out of the x initial, which is 8. Okay, my starting point is I'm starting with figuring out how much can it change from 8 to some other point. The dx What's the dx, or how much could my edge be off by? How much could my edge change by? 0.1. Do I know if I'm off 0.1 above or below? Or I don't know. So that means it actually can be plus 0.1 or minus 0.1. It's actually plus or minus 0.1. Now let's plug in. At 3x squared at 8, what's 8 squared? 64. What's 64 times 3? What's 60 times 3 plus 4? 192. Okay, so 192 times plus or minus 0.1 gives me a final of plus or minus 19.2. Let's go back and talk some units here. This was 3x squared. X is measured in what? The side was measured in what? Centimeters. So when I did 3x squared, it was centimeters squared. Dx, that's how much my length measurement could be off. How much were the units on that? Centimeters. So altogether, centimeters squared times centimeters is centimeters cubed. Does that make sense for an error in volume calculation? All right. That then is the estimated how much my volume could be off. If I just was off by 1/10 of a centimeter, my volume could be changing by as much as 19 cubic centimeters. Try surface area and see if you get the idea. Same cube, same starting point, same error, but this time you're trying to figure out how much could your area, surface area, be off by. Last class, I was happy with the calculus. I was so woefully sad about the geometry. Had a lot of people say the surface area of a cube is 4x squared. That makes me want to leave. Okay, so everybody all at once say your answer. Plus or minus? 9.6 centimeters squared. I like it. Now, if you did not get that, let's see where we are in error. Let's start. I probably should have in the past problem started with the equation before I went to the calculus. Let's start with the equation. What's the equation for surface area of a cube? 6x squared. Does that hang with 2 area of the base plus perimeter of the base times the height? What the heck? I thought that was a thing. Well, what's the area of the base? X squared. What's the perimeter of the base? 4x times the height. So you get 2x squared plus 4x squared. It's 6x squared either way. It's just which one's easier to run calculus on than 6x squared. This holds true. I don't want you to feel like I'm throwing something new at you. It's just this is easier. The calculus then that I should see is delta S is approximately equal to dx, which is found by S prime at some initial point times an amount of change in x. At that point then you take the derivative. What is the derivative? 12x. You don't rush into putting in the number. You say, here's the general derivative, 12x, and I'm about to evaluate it at 8, and then the dx is plus or minus 0.1. What is 12 times 8? 96 times plus or minus 0.1. That is indeed plus or minus 9.6. X units are centimeters, error units are centimeters, so the units then follow to be centimeters squared. Which makes sense. Okay. How'd that go? Good? All right. Let's then go to